Good morning, welcome to Currents Convert. In this video, let us study spectrophotometric titrations. It is also called photometric titrations. There are 5 types of curves, photometric titration curves, and also discuss the principle and applications. Okay, what is the principle of spectrophotometric titration? It involves measurement of absorbance as a function of titrant added. Okay, in this titration, the absorbance of the analyte solution is measured with the addition of titrant added. Okay, it is based on Beer's law. According to Beer's law, the absorbance is equal to epsilon Cl, where epsilon equal to molar absorption coefficient. It is a constant for a given substance. It is the concentration in moles per liter. L equal to path length, this length. The path length is constant in this case. Equal to absorbance is equal to log I naught by IT. Okay, this is the I naught is equal to intensity of the incident beam. This is the intensity of the transmitted beam. Therefore, a fraction of the light is absorbed by the sample analyte. Now, what is the condition for spectrophotometric titration? Okay, at least one of the reactant or titrant or product or external indicator must absorb light. Okay, at least analyte or titrant or product or external indicator. Okay. Fourth point, since the path length is constant and epsilon molar absorptivity is constant, absorbance is directly proportional to concentration of the analyte. Okay, and a photometric titration curve is obtained by plotting absorbance versus titrant added. Okay, there are two straight lines obtained. The intersection point gives the equivalence point or end point. Okay, there are 5 types of spectrophotometric curves obtained depending on the optical absorbance of analyte, titrant, product or external indicator. Okay. First, type A. In this case, the analyte only absorbs light. Product or titrant, they do not absorb light. In type B, the titrant only absorbs light, whereas the analyte and product do not absorb light. In type C, the product only absorbs light. In type D, both the reactant and titrant absorbs light. In type E, external indicator added absorbs light. For example, in acid-base titration, phenolphthalein is used as indicator. It absorbs light. Now, volume correction term. It is very important. Okay, the measured absorbance is measured absorbance is A observed, and corrected absorbance. See, when you plot corrected absorbance versus volume of titrant added, then only a straight line is obtained. Okay, so we need to do volume correction. What is volume correction? That is V, capital V plus small v by capital V. V is the initial volume. We have taken, for example, in the titration cell 5 ml. We add 0.1 ml. Okay, volume of titrant added. Okay, so A corrected is equal to A observed measured into V plus V by V. Let us see the animation of these 5 types of titration curves. Okay, now let us study in detail type A. In type A, the analyte, the reactant only absorbs light. For example, in the burette, thio is taken. Okay, in the in the titration cell, iodine plus Ka plus charge. Okay, it gives deep blue color, so the absorbance is higher in the beginning. As titrant is added, thio is added, what happens? Iodine is consumed, therefore the color decreases, and at the end point the color disappears. So after the end point, thio does not absorb. So in this case, the analyte only absorbs light. The product, either product or titrant, they do not absorb light. Let us see type B. In this type, the titrant only absorbs light. For example, let us take ferrous in titration cell and KMnO4 in burette titrant. Okay, so ferrous ammonium sulfate does not absorb light. Okay, does not absorb light, and on adding KMnO4, ferrous is converted into ferric and MnO4 is converted into Mn2 plus. They do not absorb light. The products and analyte do not absorb light. And at the end point, after the end point, any excess of KMnO4 produces color, so the absorbance is increasing with the titrant added after the end point. Okay, let us now see type C. In this, the product absorbs light. Okay, for example, let us take ferric alum solution in the titration cell and potassium thiocyanate in the burette. Okay, ferric does not absorb light. Okay, and potassium thiocyanate also does not absorb light, whereas the product on titration, red color complex is formed. Okay, as a result, the absorbance increases, and after the end point, there is no increase in absorbance because the titrant does not absorb light. Type D, in this case, both the reactant and the titrant absorb light. For example, potassium ferrocyanide, it is yellow in color versus KMnO4 taken in the burette titrant. Okay, so the yellow color decreases due to oxidation. Ferrocyanide is converted to ferricyanide, and then after the end point, there is an increase in absorbance due to the pink color of KMnO4. Okay. The final type E, external indicator. In this case, external indicator absorbs light. For example, let us consider acid-base titration. It can be carried out by using spectrophotometric titration. Okay, using phenolphthalein as indicator or any methyl orange as indicator. Okay. Now let us take, for example, in the acid as titrant and sodium hydroxide in the titration cell. Okay. Now plus phenolphthalein, a drop of phenolphthalein indicator, it gives pink color, so the absorbance is higher in the beginning, and okay, and at the end point, okay, till the end point there will be pink color because of sodium hydroxide is present. Once all the sodium hydroxide is consumed, okay, the pink color disappears at the end point. So you see there is a sharp reduction in absorbance. Okay, and then after excess addition of HCl does not change the absorbance. Okay. Okay, let us now see the instrumental setup or procedure and advantages. These titrations are performed using a spectrophotometer. We need spectrophotometer or photometer, and then the titration cell we need or vessel is kept stationary with the fixed path length. The path length is fixed. The instrument the instrument is set to a suitable wavelength where there is absorption maximum. Okay, so the wavelength is fixed. Then the radiation passes through the analyte solution to the detector to measure the absorbance. Then no need to measure the true absorbance, since relative values, that is change in absorbance, are adequate or enough for endpoint detection. Okay, so we do not worry about true absorbance. We are interested only in the change in absorbance, relative values only. Okay, then once we started titration, the instrumentation settings should not be changed. Okay, titration data are then collected without changing the instrument settings. Photometric titration are often more accurate than direct photometric determinations. Okay, because why it is more accurate than direct method? Because we measure several absorbance data to determine the endpoint, whereas in direct method we measure only one absorbance. So this is one advantage, so that it gives more accurate result. And then furthermore, the impurities the colored impurities in the reactant does not affect the analyte, does not interfere, does not affect the result, because we measure only a change in absorbance. And then no calibration curve is required, whereas in other methods we need. Let us now determine the concentration in a mixture, determination of mixture of copper 2 plus and bismuth 3 plus. Using spectrophotometric titration, both the cations present in the mixture can be estimated or determined. This is the photometric titration curve and measured at 745 nanometer. Okay, so in the big, let us take 5 ml of copper and bismuth cations in the titration cell. Okay, and add EDTA in the burette. Okay, on adding EDTA, bismuth forms EDTA complex, because bismuth EDTA complex is more stable, so it is formed first, which is not absorbing. Both EDTA and bismuth EDTA do not absorb, therefore there is no change in absorbance. Okay, once all bismuth has consumed, copper, okay, started reacting with EDTA to form copper EDTA complex, which absorbs light. Copper EDTA complex absorbs light, so the absorbance increases. Once all the copper has consumed, at the endpoint or after endpoint, there is no increase in absorbance or no change in absorbance, since EDTA does not absorb light. So we have obtained two endpoints. We can easily estimate the copper ion and bismuth ion in the mixture. Thank you for watching. Please share and subscribe. Thank you.